welcome back to lecture series on aerospace propulsion. So in the previous lecture, we were discussing about the compressor. What is a compressor? What is the function of compressor? And where do we use this compressor? And what is the operating principle of a single stage axial flow compressor? And then we have seen how a pressure rise is happening across a single stage axial flow compressor and all. We have discussed in the previous lecture. So what we are going to discuss in today's lecture is that we are going to first draw the velocity triangle for a single stage axial flow compressor. From the velocity triangle, we are going to find out what is the equation for pressure rise across a single stage axial flow compressor. And we are going to see what are all the parameters it depends on in order to rise a pressure rise across a single stage. Okay. So let us take an axial flow compressor. Okay. So which is having a constant casing diameter. Constant casing diameter means you can see that this outer casing is having a same radius throughout it distance. You could see basically it's a multi-stage axial flow compressor. In this condition we have taken here is that our type of axial flow compressor we have taken here is the compressor which is having a constant casing diameter. See, from here to here it is constant. But when you look at the blades, either rotor blade or stator blades, its size is decreasing. But when you look at the hub is designed in such a way that when I'm going to measure the mean radius, it is going to be constant. So the type of compressor I'm going to take here is that mean radius is constant. Okay. As well as our casing diameter also, it is going to be a constant. So in this, I already told you, in a compressor, the first will be starting with the rotor followed by a stator. This rotor and stator we call it as the a stage. Okay, but before your rotor, in the first stage we have something called a inlet gate vanes. Okay. So what is the purpose of this inlet gate one and all we are going to see in later section. But any compressor, modern day compressor, if you see, you will have something called IGV or inlet gate vanes, okay, which is going to control the parameters of flow entering inside your axial flow compressor. Okay, this is a velocity triangle. Okay, so velocity triangle for flow at the inlet of your rotor, exit of our rotor, and then exit of your rotor will be given as the same input to the stator, and then we have the velocity triangle for the output or outlet of our stator. Okay, so here we have three velocity triangles. Okay, so one is at the basically outlet of our inlet gate vane. So I have taken a first stage of my axial flow compressor. So that means we'll have an inlet gate vanes, flow will be passing through, will come out certain properties. So what is the C, W and all we are going to see. We have three velocity triangle. In the velocity triangle also, a very important velocity triangle in this, we have to take velocity triangle of our rotor alone mainly. Okay, because in the stator we don't have any work input or work extraction, we are not doing anything. So there is not much of change happening across your stator. There's a simple conversion is happening, whereas the work input is given in the rotor. So we are going to mainly concentrate on the velocity triangle of our rotor. Okay. So on the velocity triangle, where I'm going to draw is that at the mean radius location. You see, if I'm going to take these rotor blades, okay, here you will have a different speed. At the tip, you will have the different speed. So in order to have a common condition, what I'm going to do is that I'm going to draw the velocity triangle at the mean radius location. In that mean radius location, the velocity or speed at which my rotor blade is rotating is capital U. So in this direction, my rotor blade is rotating. Okay. Now let's say if you see the velocity triangle, we have two velocity components. One is we denote by C, another one is we denote by W1. So what is this C and what is this W? Is that C we call it as the absolute velocity and a W we call it as the relative velocity. So what is this absolute velocity and what is this relative velocity? Is that absolute velocity means it is the velocity at which your flow is entering inside your rotor. Okay. Now, if you take the rotor, basically it is rotating with certain speed. let's say your flow is coming with 100 meter per second, that is absolute velocity. But the same flow, when it is moving over this rotating blade, its velocity is going to be different. That velocity, what we call it as the relative velocity. Relative velocity means with respect to this moving or rotating rotor blade, what is your flow velocity? That's what we call it as the W1 or relative velocity. And similarly, we have two angles, an alpha 1 and a beta 1. So what is this alpha 1? It's the absolute angle, and beta is the relative angle. Okay, so what is this alpha is? Basically, it is the angle between axis of my compressor to the absolute velocity component. This is what we call it as the alpha, that is absolute angle. And the angle between axis and the relative velocity, we call it as beta. So the number 1, 2, 3 and all represent. 1 represent the inlet of the rotor, 2 represents the exit of rotor, and same 2 represent the inlet of a stator, and 3 represents the outlet of our stator. Okay, so now we are going to take a single stage axial flow compressor. So I'm going to just consider only a single stage. Okay, so here it's like enlarged version of our velocity triangle. This is at the inlet of our rotor, and this is at the exit of our rotor. As I already told you, we are going to mainly focus on what is happening to this velocity across our rotor blade, because there only we are increasing the pressure of our flow. Okay, so here this CA, okay, what is this CA is basically, I'm going to call it as it is the axial component, okay, or axial velocity component. CA is represent as or called as axial velocity component. Okay, it's the axial component of your absolute velocity as well as axial component of your relative velocity. And what is this CU is basically, it is the tangential or whole velocity component. What is your CU? Basically, it is the whole velocity component. Okay, when you see this velocity triangle, you can see when the flow is passing through our rotor blade, as I already told you, how does the pressure is happening across your axial flow compressor is that when the rotor blade is rotating, it is transferring its momentum to the incoming flow such that the absolute velocity of your flow is being increased. Okay, if you take this right angle triangle, okay, so how I can increase this component, basically how I can increase the hypotenuse value? Either I can increase the tangential component, or either I can increase the axial component. Okay, so what is happening across the rotor blade is that when the flow is passing over your rotor blade, what is happening? Your relative velocity is being reduced. Whatever the relative velocity is reduced, it is added to the absolute velocity. How the absolute velocity is increased? That see, when your flow is passing through your compressor, your rotor blade is rotating in this direction. Okay, so when it is rotating, basically the component it is adding to your incoming flow is basically it is a whole velocity component or tangential velocity component. So you can see here how my absolute velocity is being increased is because by increase in the tangential velocity component. Okay, so I'm going to take either at the inlet or exit of my rotor, the speed at which it is rotating is, I'm going to take it as u. That means whatever the change is happening, the decrease in the whole velocity decrease in the relative velocity is added to the absolute velocity. How? The tangential component of the relative velocity is converted into tangential component of our absolute velocity. That's how we are able to increase the velocity. So this velocity will be converted into later by pressure in the either in the compressor like rotor itself, or it may happen in the stator. Okay. Now, this I already told you. Your flow is entering with an absolute angle of C1, which is making an angle of alpha 1 to the axial direction. Okay. So when this flow is combined with the rotational speed of our rotor, the relative velocity will become W1, and the angle it is making is going to be a beta 1. So when the air is passing through this rotor blade, what is happening? Your absolute velocity, that is C2, is absolute velocity at the exit of our rotor blade, which is increasing. So you'll have at the exit of your rotor, your C2 will be greater than C1, and relative velocity will be reduced because this relative velocity is the one which is converted into absolute velocity. So your W2 will be less than W1. That means your beta 2 will be less than beta 1. Okay, your alpha 2 will greater than alpha 1, whereas your beta 2 will be less than beta 1. So now I'm going to assume the condition that the alpha 3 is equal to alpha 1. So what is the meaning of this alpha 3 is equal to alpha 1 is that the flow absolute angle at which your flow enters in the first stage will be maintained constant throughout the consequence adjacent stages. For example, if a flow is entering at 10 degree at the first stage, when the flow is passing through the rotor and then it is passing through the stator, your stator blade will be positioned such a way that once again your flow will enter at alpha is equal to 10 degree in the next stage. So that's what alpha 3 is equal to alpha 1. Now, as I already told you, what is the purpose of this velocity triangle is that we are going to find out what is the work done, and for the given work done, how much amount of pressure we are able to rise across the single stage axial flow compressor. That's the purpose of drawing this velocity triangle. So I'm going to take the velocity triangle at the inlet. So this is our velocity triangle at inlet. So from this, if I'm going to take, let's say, tan alpha 1, what will be a tan alpha 1? Opposite side, that is Cu1 divided by adjacent side. What is your adjacent side? That is Ca1. Right. That's what I wrote here. Cu1 divided by Ca1. Similarly, if I'm going to take the relative angle, that is tan beta 1 is equal to, in this, what is your opposite side? That is going to be capital U minus Cu1, because I just need only this component, right? So Cu1 divided by Ca1. Okay, this is tan beta 1. Similarly, if I'm going to take the velocity triangle at the exit of our rotor blade, so you'll have tan alpha 2 is equal to Cu2 by Ca2, and tan beta 2 is equal to, what will be your tan beta 2? That will be once again U minus Cu2 divided by Ca2. Okay, so we have this from the velocity triangle, we got this 4 equation. So from this is from the velocity triangle at the inlet, we have this equation. Suppose if I am going to add these two equations, what I'll have? Tan alpha 1 plus tan beta 1 will be Cu1 by Ca1 plus U minus Cu1 by Ca1. So here if I am going to add it, this Cu1 and Cu1 will be cancelled out. You will be left out with tan alpha 1 plus tan beta 1 is equal to U by Ca1. Okay. Similarly, if I am going to take the velocity triangle at the outlet, we have this tan alpha 2 is equal to Cu2 by Ca2 and tan beta 2 is equal to U minus Cu2 by Ca2. So we have just made use of the trigonometric relations. If I am going to add these two, tan alpha 2 plus tan beta 2 will be Cu2 by Ca2 plus U minus Cu2 by Ca2. The Cu2 and the Cu2 will be cancelled out. You will be left out with tan alpha 2 plus tan beta 2 is equal to U by Ca2. Okay, we have tan alpha 1 plus tan beta 1 is equal to U by Ca1. Tan alpha 2 plus tan beta 2 is equal to U by Ca2. Okay, when we take the nowadays compressor, we will design our compressor in such a way that your Ca is equal to Ca1 is equal to Ca2. So what does that mean? Your axial velocity component will be remain constant. So the thing or the velocity component which we are going to change is only the tangential component or whole velocity component. So if I'm going to apply this condition, I can write tan alpha 1 plus tan beta 1 is equal to tan alpha 1 plus tan beta 1 is equal to U by Ca. Similarly, tan alpha 2 plus tan beta 2 is equal to U by Ca. So I can write tan alpha 1 plus tan beta 1 is equal to tan alpha 2 plus tan beta 2. Okay, so this is what result we are getting from our velocity triangle, which is equal to U by Ca. Okay, so this is the equation we are getting after applying the condition. Okay, that is, if I am going to assume the axial velocity component at the inlet and outlet of my stage, that is Ca is constant. So it means Ca is equal to Ca1 equal to Ca2. Okay, now what kind of process we are assuming? Basically, it is the we assume the process across our compressor is isentropic. Isentropic means it is the reversible adiabatic process. Okay, so if I'm going to take my process as adiabatic means, then I can say from the thermodynamic relation, the change in the enthalpy. Okay, so the change in the enthalpy across your rotor will be equal to what is the work done on the rotor. So that is, if I'm giving some amount of work input to my rotor, obviously there is going to be a change in enthalpy of my flow. So I'm going to write, or I can write the change in enthalpy delta H naught. That is the enthalpy change across the rotor, because we are not giving any work input in the stator. In stator, just a simple, that is, dynamic pressure is converted into static pressure, whereas in the rotor only we are rotating. Basically, that is the work input we are giving. Because of this rotation, the enthalpy of our flow is getting changed. So I can write the delta H naught, that is change in enthalpy, is equal to, this is per unit mass flow. I'm going to assume a unit mass flow rate is passing through our flow. So here you see what is this U2 into C2, CU2. Here I am rotating my rotor blade at a velocity of U2. When I rotate this, what is happening? Its tangential component is changing to CU2. Similarly, the rotation speed of my rotor at the inlet is U1, and its relative velocity, that is tangential velocity component, is C1. You could see how this U2 and CU2 is going to give me work done or change of work done is that. So I said it is unit mass flow rate. So what is the unit for unit mass? Mass flow rate is kg per second. Your U2 is on second meter per second. Your CU2 is on second, it is meter per second. So what do we have? Kg meter per second square into meter per second, that is basically it is Newton meter per second. So which is force into velocity. Okay, so what is your force into velocity? Force into distance will give you work done, and force into velocity will give you rate of work done. Basically, that is the power. So this equation for the given power, okay, or for the given change in the enthalpy, this much amount of change is happening to your flow field. Now, we have already assumed that at the mean radius location, only we have drawn our velocity triangle, and we already stated the RPM or speed at which my rotor blade is rotating is constant. So your U1 is equal to U2 is equal to U. So I can write this equation, delta H naught is equal to U into CU2 minus CU1. What is the CU2 minus CU1? We already told you your CA is not at all changing. So whatever change is happening is the work input I am giving to my rotor is directly converted into change in the tangential velocity component. So you CU2 minus CU1. Okay, so I can write the specific work input, okay, from the thermodynamics relation. I can write the specific work input equation is Ws is equal to, that is change in the enthalpy across the stage. So what is the enthalpy at the outlet of your stage is H03, and what is the enthalpy at the inlet of our stage is H01. I can write this as H02 minus H01 because I already told you there is no work input is given across your stator. That means your H03 is equal to H02. So I can write H03 minus H01, that is for entire stage, will be equal to what is happening across your rotor alone. So I can write H02 minus H01 is equal to U into Cu2 minus Cu1. Okay, so we have H is equal to Cp into T. So I can write H0 is equal to Cp into T0. So the specific work input Ws is equal to Cp into T02 minus T01. Here I am going to maintain my Cp as constant because there is not too much change in temperature is happening. So I can assume my Cp to be constant. So Cp into T02 minus T01, which will be equal to U into the Cu2 minus Cu1, I can write as delta Cu, that is change in the tangential velocity component of your absolute velocity. So what is this Cu? Basically it is the tangential component of your absolute velocity. So U into delta Cu is equal to Cp, this T02 minus T01, I can write it as delta T0. Okay. So from this I can write my delta T0 is equal to U delta Cu divided by Cp. Okay. So if I'm going to divide this equation by T01, so what I'll have delta T0 or delta T0 divided by T01 is equal to U into delta Cu divided by Cp into T01. Okay. Now what I'm going to do is that I'm going to write down this delta Cu in terms of our flow velocities, that is we have alpha 1 and beta 1. Okay. So from the velocity triangles we have seen your tan alpha 1 is equal to Cu1 by tan alpha 1 is equal to Cu1 by Ca. Okay. So from this I can write Cu1 by Ca means from this I can write my Cu1 is equal to Ca tan alpha 1. Okay. Similarly, I can write in terms of tan beta also. So if I'm going to substitute, what is your delta Cu? Your delta Cu is Cu2 minus Cu1. Right. So from the tan alpha 2 I can write Cu2 by tan Ca. From that I can write my Cu2 is equal to Ca into tan alpha 2. Okay. So what is the equation? Your delta Cu is equal to Cu2 minus Cu1. So what is our Cu1? Ca tan alpha 1 minus, Ca tan alpha 2 minus Ca tan alpha 1. Okay, or you can write it as Ca tan beta 1 minus tan beta 2, because here Ca is common. So I can write this equation. So I'm going to substitute. So your delta T0 is equal to, what will be the delta T0? Is equal to UCA by Cp into tan alpha 2 minus tan alpha 1, or UCA by Cp into tan beta 1 minus tan beta 2. Basically, this is the equation for change in the total temperature across your stage. So if I'm going to divide that by T01, you will have delta T0 by T01 is equal to U by Ca Cp T01 into tan beta 1 minus tan beta 2, or we have already equation tan beta 1 minus tan beta 2 is equal to tan alpha 2 minus tan alpha 1. So either you can write this equation in terms of beta 1 minus beta 2 or alpha 2 minus alpha 1. Okay. So if I'm going to define the stage total to total efficiency, that is efficiency of our compressor. What is the efficiency of our compressor? Basically it is the ratio of, we have already seen what is the definition of efficiency of your compressor. That is the enthalpy change in the ideal process divided by enthalpy change in the actual process or real process. So ideal process means your process will be across your stage will be what is that isentropic. So H03S, this S represents your process is ideal. Basically, it is an isentropic process. H03S minus H01 divided by H03 minus H01. This is the change in enthalpy happens in real case scenario. This is change in enthalpy happens in an isentropic process. Okay. Now I can write this equation as H naught is equal to Cp into T naught. So I can write Cp, everything will be cancelled out. You'll have T03S minus T01 divided by T03 minus T01. Okay. So this T03 minus T01 basically that is the change in the total temperature across a stage. I can write it as delta T naught. So in this, if I'm going to take out T0 as common and make it go to the downside, you will have T03S by T01 minus 1 divided by delta T naught by T01. We have, what I want is, what is the change in temperature. So T03 minus T03S by T01 minus 1 will be, I can write it as, it will go stage efficiency into delta T naught by T0. So I can write T03S by T01 is equal to 1 plus neta S into delta T naught by T01. This is the change in total temperature across a stage, which we wrote it in terms of this equation. Okay. So we have equation for delta T naught by T01, which is basically UCA by Cp into T01 into either tan beta 1 minus tan beta 2 or tan alpha 2 minus tan alpha 1. Okay. So now here this T03S by T01 represents the isentropic process. We have the isentropic relation. T naught by P naught by P is equal to T naught by T power gamma by gamma minus 1. This is the isentropic relation. Okay. So we have T03S by T01. So I can, from that I can find out what is the P03S by P01. So your P03S by P01 will be equal to 1 plus neta St delta T naught by T01 power gamma by gamma minus 1. So we have this delta T naught by T01, which is UCA by CPT01 into tan alpha 2 minus tan alpha 1 or tan beta 1 minus tan beta 2. So from that I can write the equation for pressure rise. What is this pi stage? Basically P03 by P01. P03 by P01, it is the pressure ratio across a single stage axial flow compressor, which we represent by pi. Your pi stage is equal to 1 plus neta St into UCA into tan alpha 2 minus tan alpha 1 divided by CPT01 whole power gamma by gamma minus 1. Either you can write in terms of alpha 2 minus alpha 1, or I can change this equation to tan beta 1 minus tan beta 2. Okay. So from this I can find out what is the pressure rise across a single stage axial flow compressor. Okay. So what we have done in this lecture, we started off with the velocity triangle. What are the different velocity components available and which velocity component is converted into which component. We have seen your absolute velocity is increasing across your rotor. Meanwhile, your relative velocity will be decreasing. And how your absolute velocity is increased, the tangential component of your relative velocity is converted into tangential velocity component of your absolute velocity. So then we have seen the work done equation for work done from thermodynamic relation. We wrote that in terms of the velocities, and then from that we got what is the temperature change. We got an enthalpy change equation. From that we found the temperature change, and we utilized the isentropic efficiency relation. From that we got what is the equation for pressure rise across a single stage axial flow compressor. Okay. So with this, I'll end this today's lecture. So in the next lecture, we are going to continue with what all the parameters this particular pressure rise across a single stage compressor is depends on, or what are the parameters which is basically going to limit the pressure rise across a single stage axial flow compressor. We are going to discuss in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.